All right, so welcome to rational functions. Okay, so to give you a vision of what we're doing, we've been talking about polynomials, right? And a polynomial is like a function that has a bunch of x's with a bunch of powers. But the key is the powers are always positive whole numbers, or maybe x to the 0, which would be a constant. And because of that, you never end up with an x in the denominator. Or because it's not a fraction like x to the half, you never end up with the square root. And if you get rid of denominators and square roots, then you really don't have any places where the graph could have a limited domain. All right? Which is why polynomials just cruise along like this. Sometimes they're simple like parabolas, or maybe really simple like a line, but most of the time they're just doing this kind of stuff. Well, that's a polynomial. But if I take a polynomial and divide it by another polynomial, and remember, that could be really simple too. Like it could be something as simple as, and you know what this looks like, 1 over x. This would be like the polynomial y equals 1, a constant. Y equals 1 over y equals, like just a simple x term. And what do you notice about 1 over x? It doesn't just do this forever left and right. What's it do? It's got a vertical asymptote in it. It's got a place where this is undefined. Okay? So rational functions, because they have denominators with lots of x's, sometimes will have vertical asymptotes, and also sometimes they'll have what we call holes. And a hole, so you already know what a VA looks like, right? A VA is just a place in the graph where the curve cruises along, but the closer it gets to the asymptote, what does it have to do? It starts following it up or following it down on either side, right? It never just hops over it. That's a vertical asymptote. So they behave like this. Well, what if I had a graph that looked something like this? Well, now I've got a spot in the graph where if I plug 0 in, it's undefined, but also if I plug 2 in, it's undefined. Do you see that? But because when I plug 2 in there, when I plug 2 in there, I'm not going to get a vertical asymptote because technically these cancel. And I'm left with the graph that we're already familiar with. But that 2 is still a problem because in the original problem 2 is not allowed. Well, if you ever have a factor like this in the denominator that is also in the numerator that cancels, then at that x value of 2, you're going to end up having what we call a hole. And a hole kind of looks like that. So there are both places where the graph doesn't exist, but one of them has the behavior of an asymptote, which means it's going to follow it up and down, or maybe all the way up or all the way down. And then another one, like a hole, just hops right over. And we'll talk about how to find these. Now, here's what you need to understand, in addition to that. When you're dealing with these ugly graphs like this thing, okay, you're going to take a look at this, and I'm going to say, hey, anybody have an idea what this graph looks like? And you're going to go, dude, I don't know. I know I can't plug a 3 in the bottom. So if I can't plug a 3 in, that means there's either a vertical asymptote or a hole in this thing. There's the VA. There's the hole. We'll talk about what that means. But this graph still has a general look. And the way to have an idea about what that general look is to figure out what its slant asymptote or horizontal asymptote or oblique asymptote. Get an idea of what it's looking like. And this is kind of the idea of it. What if I told you I had 24/5 dollars, and I got 24/5 dollars? Well, that's kind of stupid, right? How do you figure out about how much money? Let me give you a better example. I got 21/5 dollars. About how much money do I have? I got about $4, right? I got about $4. Now, the mentality of I've got about $4 is kind of like what we're going to do with the slant asymptote. A slant asymptote is telling me, and it's not always slanted, but that's the majority of what we deal with in this class in AP Calc. Or horizontal. A horizontal or slant is about what this graph looks like. Because what you're going to find out is, when I graph a graph like this, you may look at this and go, oh man, that's a weird looking graph. It's a weird looking graph from like -5 to 5, -5 to 5. But if I start zooming out on a graph like this graph right here, if I start zooming out on it, you know what I find? that the graph really looks like a horizontal line once I start zooming out. So it's kind of like 21/5 dollars is about $4. It's kind of like me saying a horizontal asymptote is about what this graph looks like. Now, is the horizontal asymptote the graph? No. The graph is all of it. The graph is that. Right here, do I really have $4? No. What I have is 4 1/5 or $4.20. The exact amount that I get is the amount that I get when I actually go and do, when I just look at this fraction and don't cancel anything. That's the exact graph. But what we want to do is have a general idea about what this graph is doing and how it's behaving. Because when we get to calculus, we're going to start doing limits. You're going to do it actually this year at the end of the year, barring a meltdown like last spring. So when we look at limits, I'm going to ask you a question like, hey, how's this graph behaving? And you know how we can look at polynomials and we can look at powers and the sign of the lead term to tell what it's doing to the right and the left? Well, what a graph is doing to the right and the left, whatever it's doing, that's its limit to infinity. So we're talking about it in pre-cal language, but eventually we're going to talk about calculus language. And I want to know what this graph is doing. And to know what it's doing, I want to know about what I have. And the way you can always tell is the same thing I would have done here. If I want to know about what I have, and you may or may not have thought, you may not have realized you did this, but you have to divide 5 into 21 to see what you get. Right? And if I toss the remainder, that's about what I have. Now in real life, if this had been like 24/5, you would have said probably about $5. But in what we're kind of rounding down and tossing the remainder, that's what our slant asymptote is going to be. So I want to talk about that right now. If I want to have an idea of what this looks like, just if I wanted to have an idea about how much money I have, all I have to do is take the denominator and divide it into the numerator. And whatever I get, not counting the remainder, that's how this graph is going to behave to infinity and negative infinity. All right? So you'll see that. Now there are going to be some things that we're going to do to make our lives, some little patterns we're going to notice, but I want you to see this up front. So let's take a look. If I gave you this ugly fraction, and I'm guessing again that you have no idea what that thing looks like, okay, because you're just getting started. Now I can tell that 3 does not exist in there. I do know that. But watch this. If I take the denominator and divide it into the numerator, and I chose to use long division, but you could have done synthetic here. I go in there, remember how you do long division? X times what gives me that? 3x. 3x times all of that gives me this, and then I change the signs. Add. Of course, this always goes away, and I get 4. Drop down to -2. X times what gives me 4x? 4. Now again, I went ahead and finished this off and found the remainder was 10. So I can rewrite this as that. So this is the same thing as that, because I kept the remainder, right? Just like 21/5 is the same thing as 4.2 or 4 1/5. They're the same, but it's about 4. So if I want to know about what this graph looks like, I toss the remainder, and this graph looks like a line. Now, is it a line? No. But it looks like one. Does it look like one up close? No. But as you zoom out forever, this graph is going to look like y equals 3x plus 4. And that, because it's a slanted line, not a horizontal line, is what we call the slant asymptote. Now you're not always going to end up with a slant asymptote. What if I divide and I get something x squared? What do you think that looks like? Probably looks like a parabola. And you can actually have a parabolic asymptote. You can have a graph that literally looks like this as you're going towards infinity or negative infinity, and maybe as it comes in here towards the middle, it might go, and it might have another craziness going on. It can totally look like this. It can have a hole in it in a couple spots, and nobody on the planet would ever look right here and go, oh, parabola, right? You would never look at that and think it's a parabola. But as you zoom out, the more you zoom out, the more it resembles that. And that's what an asymptote does. It tells you what the graph is doing as you go forever left and forever right. And what you have is always dependent on these powers. Because if the power is 1 bigger, when you divide in there, you get a line. If the power is 2 bigger, when you divide in there, you get a parabola. And we're not going to do a whole lot with parabolas and other kinds of asymptotes. But we're going to do a ton of slants, and we're going to do a ton of horizontals. All right, so we're going to learn some rules on that that's going to make your life kind of easy. But anyway, I wanted to show you this in a chart and also on some graphs so that you believe me a little bit. Even though some of you are like, it's Tuesday, after a 3-day weekend, I'm just barely awake. It's okay, hang in there. So check it out. I'm going to plug values into the original function, which would be the same thing as me doing that because that includes the remainder. That's the same thing as this. But I'm also going to plug values into the slant asymptote, right? This part without the remainder. Now look, plug in the 5. What do I get for each y value? 24 and 19, totally different. 5 units apart. You would never confuse these two at this point. But look what happens as I start going further out. 10, 20, 50, 100. Look at the y values. Instead of being 24 and 19, 5 apart, now they're 35 and 3/7 and 34. 64.5, 64. 154.2, 154. And even way out here at 1,000, 3004.01, 3004. So the further I get out, the more the slant asymptote values are the actual driving force of this graph. So again, if I want to graph something, I can always plot points. But if I want the general look of something, I can figure the asymptote out by just dividing and tossing the remainder. And it's a big question at math tournaments, believe it or not. It's a big question on the AP test because they're going to talk about end behavior. And if I asked you, hey, what is this thing doing as you head to the right? Is it going up? Is it going down? Is it flattening out? If you're listening, you know this. What's it doing? Why up to the right? Okay, and don't just look at that positive first coefficient because that could be negative. But that positive first coefficient, right, is positive. It must be going up to the right. And because it's odd, it's going in the opposite direction. And you know what lines look like, right? So you know right now what this graph is doing because you're looking at that slant asymptote. And if you look at the graph of this, which I have on the other side, what I didn't put in there was the x equals 3 VA, but there's actually a vertical asymptote right here at x equals 3. And you can see that, right? And I've also put a little line in there representing the slant asymptote, the 3x, what was it, 3x plus 5? So there's your slant, and there's your vertical. And look, would anybody on the planet ever look at this graph and go, oh, line? No, because you're looking too closely. But as I start zooming out, and granted, negative 30 to 30 is not super close, but if I go negative 10 to 10, you can't see this top part, so I enlarge it a little bit. But look, as I go further and further out, it doesn't mean the asymptote goes away, right? There's still a VA right here, but as you go further and further out, really, what do you see? You see the line. And it's not actually the line, it's just really, really close. But that's what asymptotes do. It draws the graph to itself, and it determines what happens at the end behavior, to infinity and to negative infinity and beyond. Right? So the idea of an asymptote is just what the graph looks like. It's not what you're going to be graphing for me, though. Because you're going to be graphing like negative 10 to 10. And all kinds of chaos is going to ensue right there in the inside. So your graphs are going to look totally bizarre, but you will have that slant in there. And that slant will just start to show you something, or maybe a horizontal. But the first thing you're always going to want to figure out is holes, but then beyond that, you start looking at slants and things like that. And I do want to mention obliques. And I did some studying on oblique. I used to just trust what the book said about obliques, and then, or what books said, but as I've taught decades and gone through different books, they all say different things. So I really got on a big search. Some people say an oblique asymptote is just any asymptote that it follows to infinity or negative infinity. Some people say that an oblique asymptote is something that's a higher power, like higher than a slanted one. Because honestly, sometimes a linear asymptote that slants, we'll call a slant. A parabolic asymptote, we'll call a parabolic asymptote. A cubic asymptote, we could call that. A quartic asymptote, we could call it different names. But a lot of people just say, hey, an oblique asymptote is anything that's not a slant, that's a higher order power. So that's kind of what I say, but again, I've gone through the internet and different books, and they all seem to say something different. So you're welcome to read this. But anyway, so you can see right here, most of the time in high school, the oblique ends up being a horizontal line because they just refer to anything that is an oblique. But old school test books don't do that. They kind of say slant, horizontal, slant, and then anything else is an oblique. But whatever, I'm not going to quibble about that. So I'm saying, find your asymptote, whatever it is. Now on this first one, what do you notice about the powers? One higher on the top. So if I were to divide and it's one higher power on the top, what do you think is going to happen? What's going to happen when you do the division? You're going to have what kind of line? You're going to have an X in that line, right? So it's going to have a slope. And if it has a slope that's not zero, then it's slanted. So when I see one power higher, I know that I'm going to end up having some kind of a slant asymptote. What about, and I'll do that in a second, what about this one? I'm dividing an X into an X cubed. It's going to end up being a parabola because it's going to go in there X squared times. Now I'm going to never worry about the remainder, but I got to divide enough to be able to figure that out. What about this on number 3 where it's one power higher? Again, a slanted line, so a slant asymptote. And what about here on number 4? Still a slant because it's just one power higher. Except what am I going to be forced to do on number 4 when I divide? But I could do synthetic on 1, 2, and 3, but on number 4 I would have to do what? Long division. Okay, so real quickly, just a reminder about synthetic division. Here, I'm dividing with a 1, and I'm dividing into 2, -3, and 5. And if you remember synthetic, I add the column and I get a 2, or just drop it down. 1 times 2 is 2. Add the column, I get a -1, and quite honestly, at this point, I don't even need to find the remainder, because I'm not even going to look at that. If all I want is the slant asymptote, I'm going to say y equals 2x minus 1. That is my slant asymptote. And if I have a slant, I do not have a horizontal. I can only have one asymptote that heads towards positive and negative infinity. Well, on rational functions, on piecewise functions, anything can happen. Or graphs that act like piecewise functions, like absolute value. You know how it does one thing one way and another thing the other way? Graphs like that can do different things, but normal rational functions like we're talking about today can only have one. All right, what about this then? Do you remember, is there any difference here when it comes to doing the synthetic division? And yes, I'm going to do 1/2, but is there anything different I have to do to finish this guy up? Do what? So when I'm finished, because I led with a 2, I've got to divide everything by 2. So again, real quickly, drop the 4. Half of 4 is 2. Add. Half of -4 is -2. Add. Half of 8 is 4. I really didn't even have to do that though, because I really don't care about that. And then because there's a lead 2, don't forget to divide by 2. And then of course, don't forget to put the x, the x squared, and don't forget the y equals, because you've got to make it some kind of working function. And you end up with 2x squared minus 2x plus 4. And that is the parabola that this graph will follow. And I will not ask you to graph any of those in this chapter. If you sketch anything, it'll be a horizontal or a slant. But I may ask you to find the asymptote, or what kind of asymptote, and you would say, well, it's some kind of parabolic or oblique. And then down here at number 3, hopefully that won't be a big deal. Similar kind of thinking as before. You're going to take that -3, divide it into 4, -2, -3, and just remember, we really don't even care about the remainder. What's important is y equals 4x minus 14, and that would be your slant. And then lastly, I think I've just finished your first page of homework, just to complete this. On this one, you cannot do synthetic division. So you would be forced, but the nice thing is, even if you're thinking, oh man, I hate long division. Guess what the biggest mistakes are in long division? There are two primary mistakes. Copying the problem down wrong is shockingly number one, or at least tied with number one. Guess what the other one is? And it happens with synthetic too. Forgetting to fill in a zero if you're missing a term. Missing a power term, remember that? Okay, so right here, I'm going to go x squared times what gives me 3x cubed. And you'll see it's not a real long process like it was when I gave you these in Algebra 2, because we were dealing with changed signs, we were dealing with higher powers. It's really usually a two-step process, and you'll see that right here, look. What times that gives me that? And look, the second I write the constant down, I don't have to go any further. Why? Because we don't care about what? We don't care about remainders when we're finding asymptotes that show end behavior. So all you do is don't forget to put y equals again. Just call it a day. Okay. So far so good? So why are we doing this? I mean, that's a good question in general, but like in terms of just, why are we doing this? In terms of the math, we're finding this because this is showing me what?
How the graph behaves.
How the graph behaves heading where? To infinity, right? And negative infinity, either way. So this is helping me with my end behavior, which in your graph from negative 10 to 10 is not everything. There's all kinds of other junk that's going to be going on, you're going to see. But this will help me with my end behavior. Now, one thing I did not show you was this. I'll just give you, we'll call it example 5. What if I gave you something like this? And said determine the asymptote, whether it's slant, horizontal, whatever. And you're like, well, he told me to divide, right? So what would happen if I divided this 2x squared, blah, 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 into this 6x squared? 3. And what did I say to do once you hit a constant, like we did in number 4? Set it equals 0 and forget the rest. So is there a better way if there's a slant, or is there a way to know if there's going to be a slant? What was different about this than all the other examples? They have the same power. So if you have the same power, you know you're going to end up with a horizontal, not a slant. And could I have done something more simple than writing out this division problem to get y equals 3? So just look at the two coefficients and say y equals that, 6 over 2, or y equals 3. And that would save me some trouble. Now, with that in mind, is there any other situation? We've already talked about powers being bigger on the top. We just addressed powers being the same on the top and the bottom. What other option is there? Being bigger on the bottom? What would that mean? What if this was 2x cubed? We'll call this number 6. We still want to figure out the behavior. How many times does 2x cubed, blah, 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 go into 6x squared, blah, blah, blah? None. So in this case, if the power's ever bigger on the bottom and you bother to do the division, you would get y equals 0. Well, don't bother to do the division. You don't have to do anything except y equals 0 if the power's bigger on the bottom. Now another way to think about that, if it helps, what does this give me? Ballpark me. Just describe this value to me. Here, I'll make it harder just to think about it. Describe that to me. Got 3 seconds. Best thought. Do what? Now, describe your final answer. In terms of, oh man, super tiny. Super big. Probably big, right? Because if I get a constant that's not moving, even something like 257, which is not, I mean, if I have $257, I'm happy that I have it, but it's not life-changing money, is it? I mean, for you guys, it might be monthly changing money. It's a pair of J's or something, but it's not a whole lot of life change right here at 257, right? But if I divide it by 0.007, if I take a constant and divide it by a tiny number, it starts becoming a huge number, right? What about if I have a tiny number and I divide it by a huge number? What does that mean? Super tiny. Well, think about this. What happens to the bottom fraction as opposed to the top fraction as I start plugging in bigger x's? Like if I plug 100 in there, what happens if I plug 100 in the bottom? What's 100 cubed? 6 zeros, isn't it? 100 is 10 squared, and I cube it, I get 6 zeros with that too. 6 zeros and a 2, it's pretty big, right? Now, 100 in there, 500 minus 7. Doesn't do a lot, does it? Huge number though. What if I plug 100 in there? That's 10 squared squared. That's 4 zeros with a 6. Oh, and then 100 in there, 300, 4. These numbers have very little impact on this fraction, but the lead numbers are what impact it. And what's happening? The bottom is doing what as I move out to the right? I go past 10, 50, 100, 1,000, 1,000,000, 1,000,000,000. What's controlling the size of this fraction? What's really controlling the size of it? The denominator, because it's a higher power. So the highest power controls. So you can see right here, wait a minute, as the bottom grows faster at a higher rate than the top, what's the size of this fraction going to do? It's going to get smaller, isn't it? So that's why this is always 0. It's going to continue to shrink. And these aren't going to impact it much. Because think about it. If I give Jack 2 million, right? And then Kate goes, can I have 500? Right? I mean, me plugging a 100 in there is 2 million. Me plugging 100 in there is 500. If I just hand him $2 million and he's just nirvana, right? That's game-changing money, especially if you invest it now, let it grow for 40 years, you're a zillionaire, right? Giving Kate 500, it's not a whole lot of skin off his back. Giving somebody else $7, sure, right? This power is controlling this fraction because it's a higher power. And that's the whole idea. What happens as you head to infinity? Well, this highest power on the bottom is going to make this fraction shrink to nothing. So hopefully you kind of learned something that, oh, higher power, bigger on the top, there's some kind of slanted or oblique asymptote. Same powers, there's still something controlling this fraction, but it ends up being the coefficients. But bigger on the bottom, these fractions always go to 0 because the bottom's growing faster. And if the bottom grows faster, they're always going to 0. And by the way, if the top grows faster, they're always going to what? The top of a fraction grows faster than the bottom. What's the size of that fraction approaching? Infinity, which is what a slanted asymptote does, doesn't it? It goes to infinity, or maybe negative infinity, but it gets huge in a positive or negative way. And when they're the same power, they don't grow to infinity or negative infinity. What do? Or to 0, they approach the fraction. So hopefully that makes sense, but that's just a quick lesson on slanted asymptotes. Now, the other stuff that impacts, of rational functions, the other thing that impacts it are the vertical asymptotes. The holes, the x-intercepts, the y-intercepts, all that extra junk. And I'm going to run through that before this bell rings in 18 minutes, and maybe we can get to an example. But if you ever forget what I'm saying, which you probably will tonight, and even we're going to do this again tomorrow, except you won't be here. If you ever forget, literally look at these notes. These notes are great. Man, I don't know how to find the hole. I totally forgot. To find the hole. Okay? Go back and just read. Oh man, horizontal asymptotes. These are impossible. If only I knew how to find the horizontal asymptotes. I'm spelling it out here for you. So you're gonna know this. Okay, most people do really well on this part. The only thing that hurts people on this test is missing a key factor and it kind of snowballing on you. And I try to do my best to prevent that, but check it out. And I would go in this order if I were you, although some things you can do in a different order, but this one's not negotiable. Well, very rare. You need to identify the holes, because if you don't, you will confuse them as x-intercepts and vertical asymptotes, and that's when your graph goes to pop. Okay? So holes. We already mentioned a hole is a place in the graph where the graph is undefined. But the difference between it and a VA is a VA, as it approaches a VA, what does it have to do? Follow it up or down or whatever. Okay? But a hole just does what? Runs into it, hops out the other side. So literally, we want to cancel those holes out, and we can figure out what the graph looks like. All you have to do to find holes is to get it factored, and any common factor. Once you factored it, if you factor something out of the numerator and the denominator, there's a hole at that x value. So if I cancel out an x minus 2, there's a hole at 2. If I cancel out an x plus 6, there's a hole at negative 6. But a hole is not just an x value, it's a point. So what would you think you do after canceling it and finding the x value? How would you find the y value that goes with it? How do you always find the y value that goes with an x? Plug in the x, except if I plug it into the original function, I'm going to get 0 over 0 every time. So make sure you do what? That's right. Cancel out that factor and plug it into whatever's left. And that's how you'll find exactly where the hole is. And if you ever graph a function on your calculator that has a hole, you're not going to see a big round hole. It's going to look like it just goes right through it. But if you ever traced and entered that x value in, there would be no y value that goes with it. But on our graphs, we're going to show holes by just big open circles. And you'll see that when I'm graphing them for you as well. Okay? So again, to find a hole, if it has one, factor it up. You have a common factor, cancel it. Take the x value from that factor, just like you would use if you were doing synthetic division. Right? Set it equal to 0 to get the x coordinate. Plug it back into the uncanceled part to get the y value. And be careful about that, because sometimes that can be messy. I mean, you end up with some ugly y values most of the time. Now do that first. And guys, once you cancel out those factors, you will never look at them. Don't go, but it looks ugly if I cancel it out. Cancel them out, never use them again. If you leave them in there, you're going to confuse them with vertical asymptotes and x-intercepts, and it's going to cost you twice. Okay? And I will hopefully get to an example today. If not, we'll do a bunch tomorrow. All right, horizontal asymptotes. We just said this. When do horizontal asymptotes occur? If the powers are the same, and if the powers are the same right here, which is example 2, I just take the a value and the b value and say y equals that. Make sure you say y equals, because it's a line, right? The horizontal asymptote is a line. Don't just say, oh, the horizontal asymptote is 2/5. What 2/5? Y equals 2/5. Okay? When else do you have a horizontal? We said that, remember, it could be 0 and when is it 0? Power is bigger on the bottom. So if the powers are the same, a over b. If the power is bigger on the bottom, always y equals 0. And if the power is bigger on the top, then you don't have a horizontal, you have a what? Slant or some other oblique. In this course, typically a slant, and in calculus. So, the third example, power bigger on the top, that doesn't even have a horizontal. But remember, if you don't have a horizontal, you're going to have a slant or something else. If you have a slant or something else, then you won't have a horizontal. Because the graph can't be doing this, can it? Can your graph have a horizontal and a slant? Let's think about it. Could it do something like this? And if not, tell me why. Why can't a graph follow a slant and a horizontal? What are we talking about today? Rational functions? Doesn't pass vertical line test. I cannot follow two masters right here, okay? I can't. I'm only controlled by a slant or a horizontal or something, but never both. So even on your test, I'll say find the slant or the horizontal. So there's not, that's kind of my hint to you that there's not both, right? It's not slant and horizontal, it's just one or the other. All right? Okay, so that's that. So if your power is bigger on the top, that goes to the third one, slant asymptotes, which we've already talked about, right? But if your brain freezes and you go, oh, I forgot how to find a slant. Well, to find a slant, then divide the numerator by the denominator. The result, not counting the remainder, set equal to y is your slant. And by the way, if you've canceled holes out already, What you want to do, right? If you do that already, then your division's probably going to be okay with synthetic division. If you don't cancel the holes out, you're probably going to have to do long division, which is a little nastier. All right, and then the last couple things, vertical asymptotes. Where do you think vertical asymptotes come from? You're about to find out, but if you forget to find the VAs, all you're going to do is set whatever's left of the denominator. What do I mean by what's left? Well, you may have canceled out what? The common factors that gave you holes. Once those are gone, whatever's left, set it equal to 0. And whatever you get there, you're going to get lines. Like, so if I have an x minus 3 and I set it equal to 0, I get x equal 3. That's a vertical line. Those vertical lines, when they're set equal to 0 and solved, are your vertical asymptotes. And what do they do differently than holes? You have to follow them. You have to. You can't do stuff like this, guys. You can't go, oh, vertical asymptote, and just stop. This doesn't happen, okay? You're going to either go down or up, or maybe up, or down, or whatever. You're going to do something, but it has to behave like a VA, like a vertical asymptote thing. Are you with me? Oh, and another thing of note, did you notice the difference between a 1 over an x graph that does this and a 1 over x squared that does this? Well, if your factor in the denominator that gives you your vertical asymptote, if it has an even power, it makes the asymptote follow it on the same direction, either up and down and down. If it's an odd power, like 1 over x, different direction. Even power, like 1 over x squared, same direction. So that's something else you'll need to notice. So if I get it all factored and I go, oh, look, there's a VA, and it came from an x minus 2 squared, my VA is going to be at x equals 2, but it's either going to go up or down and down, depending on some other things. Are you tracking with me? All right. Last two things, you should already know this. How do you find x-intercepts? Plug in 0 for y and solve. I have a question. What happens the second I plug in a 0? If I plug a 0, and this will take a couple steps off the board. If I plug a 0 there, what would be the first thing to do? Pretend you're looking at something there. What would be the first thing you do to solve? So find the denominator and multiply it by both sides. What does that essentially do to the left side? Still 0. What's it do to the right side? Cancels out the denominator. What are you left with? Just that. So, what affects x-intercepts? The numerator. So, to find your x-intercepts, basically, just set each x value in that numerator equal to 0 and solve. Okay? So, sorry, to find the x-intercepts, set what's left of the numerator. Why do I say what's left? Because you might have what? Canceled something out for holes. Set whatever's left in the numerator equal to 0 and solve. Those will be your x-intercepts. There are not any extra ones. There are not any like mystery x-intercepts or unknown ones. I see people that mark them right here. They mark their x-intercepts and then they go to sketch the graph and they cross the x-axis somewhere else. And I'm like, how can you cross there? And they're like, whoa, it made sense. It didn't. That's it. You might not have any x-intercepts. Like 1 over x. 1 over x doesn't have anything in the numerator to set equal to 0 and solve, does it? Well, you didn't cross the x-axis there. So remember, your only x-intercepts come from the numerator set equal to 0 and solve. And don't leave the canceled factors in there. Because if you do that, holes will become x-intercepts. And then find y-intercepts, which is probably one of the easier things here. What do you do? And you're only going to have one. I should have said y-intercept. The y-intercept is what? The point on the curve, which way? Because if it's a function, you're only going to cross the y-axis once. All right, but how do you find a y-intercept? You plug in 0 for x. And that's pretty easy, because if you plug in a bunch of zeros, all you have left is the constant over the constant. Unless it's factored, and then you just have to multiply all that junk together. But again, it's a good idea to write your intercepts as points. I said that this was bad. I've gotten to the point now where I'm like, an AP sometimes they'll say, what are your y-intercepts? And they'll list them like this too. So I'm not as particular about that. I'd rather you write them as a point, but if you did this, does anybody know why this is bad?
Could be mistaken for a line.
Could be mistaken for a line. But if you said, hey, the x-intercept is x equals 2, people will know what you're talking about if you clarify that. So if the question asks it, but if you're ever writing them, I think it's better to write them as a point. All right, we got 3 minutes, which is not a lot of time, so I just want to throw one problem out at you, and I'm going to do number 3. So let's just walk through number 3 as quickly as we possibly can, and I'm going to sketch it, so hang on tight. So first thing, I want to find out if there are any holes. How do I find out holes? So if I factor the top, and I get x minus 7, x plus 2. Please make sure you can factor. If you don't, come see me. First step to recovery is admitting you have a problem. Okay, so if you have issues with factoring, come talk to me. Factoring up the bottom, x plus 2, x plus 1. Do you see something? At x plus 2, there's a hole, so I'm going to cancel that. And that tells me I have a hole at what x value? Negative 2. And what is the y value that goes with that? Plug it back in, and I get negative 9 over negative 1, which is 9. And you can see negative 2, 9 will not fit on this curve, but I'm going to mark it anyway just to kind of show you. Most of the time I will. And you mark it as a hole. Does that make sense? All right, now let's talk about the rest of it. Does it have a horizontal or a slant? Horizontal. So if it has a horizontal, then it doesn't have a slant. And how do I know that? Same power, and what is the horizontal? Y equals 1. Because if it's the same power, you use the coefficients. Bigger on the power, on the bottom would be y equals 0. So horizontal would be y equals 1 over 1 or y equals 1. Does it have a vertical asymptote? Vertical asymptotes, if you forget, look back at your notes. It says anything in the denominator that's left after canceling holes, set it equal to 0. What do I get? X equal negative 1. Does it have an x-intercept? I'm going to have to move quickly. More quickly. Does it have an x-intercept? Plug in 0 for y. But what did we really say? We basically said once you plug in 0 for y and multiply by the denominator, it ends up being whatever's left in the numerator set equal to 0. Right? That's all that's left. So what's my x-intercept? 7, 0. And how do we find a y-intercept? Plug in 0 for x. So if you plug in 0 for x in the original problem, you get negative 14 over 2, which is negative 7. If you plug a 0 in the factors, you get negative 7 over 1. But either way, you get negative 7. Okay, here's me sketching everything. Here's y equals 1. Here is x equal negative 1. Here is the whole negative 2, 9. Here's the x-intercept, 7, 0. Here's the y-intercept, 0, negative 7. And then here's me sketching the graph. Okay, track with me. If I'm heading in here on this horizontal, and I have to follow the horizontal to negative infinity, here I am. What are my choices? As I come in here, as I near this VA, I can either go down or up, right? Tell me why I can't go down. 2 reasons. I have to go through the hole. Give me another reason. To go down, what would I have to do? Cross. Am I allowed to cross? No, that's the only place I can cross. So just sketching it, I would say, oh, it probably looks something like that. Going through the hole. And then this side, coming from positive infinity, I'm going to have to, again, hit that point, and then also what? Now, a little thing to help, which I didn't do because I ran out of time, it says plot at least 1 point on either side of the VAs. Plot a couple points, and it'll help you get a better look at the graph. Hey, see what you can do on this. We're going to talk a bunch more about it tomorrow. Nothing new tomorrow, except practicing this more. Y'all have a good one.